Bom dia. Eu não estou vendo aqui quem é que está conectado, mas eu suponho que...
Raul, pode dar as mensagens de boas-vindas aí.
Ok, o pessoal está conectado aí, né?
Isso, exato. Exato.
Inglês?
Isso.
So, good morning, everybody. My name is Raul Feitosa. I am a professor at the Pontifical Catholic University of Rio de Janeiro. And it's my pleasure to chair today and in the next week these lectures or tutorials on Google Earth Engine. I have to say that this event is a kind of a joint initiative involving the Geoscience, IEEE Geoscience Remote Sensing Society, and the ISPRS, International Society of Photogrammetry and Remote Sensing, and it is specifically conducted by the Geoscience Remote Sensing Brazil chapter. And on the other side, we have also the Pontifical Catholic University of Rio de Janeiro. And this event is part of this class, I'd say, is part of course that is being given at PUC-Rio in this semester. It's about deep learning applied to image analysis, and it's also part of an event being organized by the Geoscience Remote Sensing Brazil chapter. This event is called the Summer School in Young Professionals. This event started, if I'm not mistaken, 6 years ago, and this is the 6th edition of this event. And even during the pandemic, thanks the effort of the leading team of the Brazil chapter, this event has been offered last year during the pandemic, also this year in this remote mode. So before we move to the topic addressed in today's lecture, I want to invite the president of the Brazil chapters, Professor Dr. Veraldo Risenberg, to add some information about the event being conducted by the chapter this year. Please, Veraldo, you may take the control.
Perfect, thank you. Let me just share here my screen. Well, welcome all. This is actually the 7th edition of the Geoscience Remote Sensing Society Young Professionals and International Society of Photogrammetry and Remote Sensing Student Consortium Summer School. Well, this year, besides webinars, we also offer roundtables and tutorials like this one today and next Thursday with some hands-on. This year's event is locally organized by 2 Santa Catarina State universities, UDESC and UNO Chapecó, because firstly, it was planned to occur presentially at the city of Chapecó, and is supported by 2 scientific societies, the Geoscience and Remote Sensing Society, the International Society of Photogrammetry and Remote Sensing, and their student branches related or directly related to young professionals. We welcome all to visit our main webpage to watch the welcome words of our rectors and presidents of the society, and also to answer the quiz of the Chapecó city and the Santa Catarina state. Both are available here in English and Portuguese languages. This year, this event is strongly supported by our state foundation, FAPESC, and two companies, Canoinhas Geoassessoria, that will make available some datasets for other activities that will be released this year, and the Instituto Gilson Volpato of Scientific Education. We have different partners that helps to promote this event, different institutions from Brazil. We offered already some webinars and already one hands-on. Last Tuesday, a roundtable about precision farming in Portuguese language. And today we will start actually with the introduction to Google Alert Engine with R, and also next week with the deep learning for remote sensing images, processing analysis using R2. I will pass now the words again to Professor Raul so that he can
Oh,
proceed actually a welcome message to our main speaker today.
okay, Viraldo, thank you very much for this introduction. I'm not sure if everybody who's connected to this event were aware of what is going on within this event, so I think it was very informative. So my task now is to introduce our main speaker. We are going to learn from the experience of Dr. Ricardo Dallagnol da Silva. There is a short bio here that I want to read. Dr. Ricardo Dallagnol is an environment engineer, and he did his master and his PhD. He finished his PhD last year. He is a very young scientist, and he did his PhD in remote sensing in the Brazilian National Institute of Space Research, INPE. Today he works as a researcher, and he's doing his postdoc in the Earth Observation and Geomatic Division at INPE. And he has experience working with many different applications in biogeoscience with focus on tropical ecology, nature conservation, and environment monitoring in the Amazon forest. So he's a specialist, an expert in conducting quantitative researches using different types of data, such as LiDAR, aerial images, and orbital images, high resolution orbital images, and he works with different methods, which includes neural networks and specifically deep learning. And I identified some times ago that we have, let's say, a demand in our group at PUC Rio, and I think this is not only for the people at PUC, a demand to that we have no experience using the Google Earth Engine. So, and Ricardo has a good experience. He did many works using this platform, and I am very thankful, Ricardo, for that you accepted our invitation to share your experience with our group. And I'm talking on behalf of PUC Rio and also on behalf of the Brazil chapter, if you allow me, Veraldo. So let's get started. I think this is enough for introduction. I think at the end, I will return to say a few words. So you can take the control, Ricardo.
Okay, thank you very much. How can you hear me well?
Yes, perfectly.
Okay,
Yes, we can hear very well. Just last but not least, let me just uh, present or introduce Daniel Augusto da Silva. He's doing a PhD at the Regional University of Blumenau, and also working with remote sensing data. And he will also help us actually to gather questions from the audience and help actually in this moderation. So, Ricardo, feel free. The room
okay,
is now yours, and we will be here in the background together with here Leonardo Biffi and Julia Cuco Dalry to support you and your activities. Thank you.
okay. Great, Veral. Thank you very much. So can you see my whole screen?
Yes, that is just a
Yes.
button in the low part. Right. Wonderful.
Okay, good. So I think we have around 40 people already watching on YouTube, and it's increasing. When I look to this direction, I'm looking to my laptop. So if you are watching out there, and you could include in the chat like where are you coming from. So this is nice. So we see who we are talking to with today. And so, as Raul introduced me, I'm Ricardo Dallagnol. I'm a postdoc researcher here at INPE, the Brazilian National Institute for Space Research. And I use remote sensing for about more than 10 years now. And Google Earth Engine is a revolution to our time. So if you're starting to use remote sensing now, it's becoming like a key skill moving on. So this is something you should learn. You should get some practice, and it will be very important for your work both on the academia and also in the industry. So before I delve in the code, I think Veraldo or someone from the organization sent you an email about the installation package and the GitHub platform here. So this github.com slash recds slash dl underline rs underline ge. So this URL, I hope the organization can send this in the chat, this link here. So this is a repository for both the code and some presentations and some data set for the today's tutorial. I have also used this material for another workshop here at INPE at the Applied Computational Postgraduate mini course, the WorkCap. And so, oops, download some. I'm sorry. And so you have here some description about the code, the link for the data set, so you can access the data. So here is this link. If you cannot find this link, you can also open the Zenodo repository manually and type in probably data set, deep learning, and my name, Ricardo. You surely find it, but the link is around here. So today we'll be using, I think, only a shapefile from this data set. If you haven't downloaded, I recommend you download it now. If you're going to come for the next session next week, it will be very important that you download this data set for the next week, where we'll be talking about the deep learning. And okay, so for today, the installation package code is right here. So if you have installed, you can still try and do it now. It will take a while, but we'll move on with the course today. So this is the code for the installation that you can find on the GitHub. So for today, we have two main scripts here. I won't have a formal presentation. I'll just use the R interface here. So we have this RGE basics script and the RGE data acquisition. We'll start with the RGE basics. So if you downloaded this, open this at your RStudio, and we shall start. One important thing inside R is this small list here that you can find at this button on the right side of source button, which shows like an index. I like to use this to find myself within the script, so this can be very useful. And before I start here, also to say I'm sorry to those who are not very known with R. I will not be able to explain every aspect of R. Otherwise, it would be another course only on R. But I'll try to explain as much as possible while explaining the main thing today, which is the Google Earth Engine inside R. So to start here, we have the start of the script. You can run the first steps here. And before you run, you should adapt this line code 2023 probably, which is the path to your environment, which you installed with the code and the tutorial I provided on the GitHub. So it should be a bit different than this, probably some username here or something like that. So I hope you got the environment installed and you can just run this. And to run, either you can use a hotkey or push the run button here. It will run. And this is like just loading a few packages, okay? So for those who are confused, this pload function here, it's something from the Pacman library, which it tries to see if this package Raster it's already installed, then it just loads the package. If the package is not yet installed, then it will install this package for you. So it's like a function to make your life easier. So we ran this first part, and we now go to initiate the RGEE connection. So if you install everything from the RGE install packages script, you should be able just to run this entire part of the initiate RGE, and it should appear this this initiation. This is Google Drive, Google Earth Engine credentials. It should appear this kind of thing that is on the console right now. So probably your username here. If you have issues with that, try to follow the script on the RGE install packages again. Sometimes there are some errors with the R packages, which are sometimes a bit pain to solve, but it should work with the strategy I put on that script. And so if you were able to load the RGE and got a similar screen to mine, please type in the chat that you were able to enter the RGE, so we know like how many people are with us. And while you do that, I'll explain like what we are going to learn today. So in every class of mine, I try to put the learning objectives. So I expect that in the end of this lesson today, you'll be able to explain and use basic operations in Google Earth Engine, filter and visualize geospatial data using the RGE interface, to acquire and download geospatial data, including remote sensing imagery, using RGE, and to apply machine learning method using the data that we download. So this last part is more or less like a bonus. I put it here because next week we'll be dealing with deep learning with the data that we download today. And so I put in the end of this lesson a machine learning, a more simple method So we can see like a result, and next week we compare with that. So I already invite you for next week for the deep learning session. And I already see that some people are able to enter the Google Earth. That's good. So what is RGE and why do I care about this? The RGE is a package that interacts with Google Earth Engine. So basically, I hope you can. Oh, I forgot to load something here. Just wait a second. It should work now. Yes, I got this. So the RGE is it's a package from R that interacts with the with the Google Earth Engine, and it does that by so we have RGEE here, and we have then an interaction with a Python API, which is translate to some codes for Python, which can talk to the uh, sorry, with the GE inside the Google interface. So the Google interface, the original one. So we use this Python API through the RGE. So that's why you had all these installation procedures. So the R can talk to the Python, can talk to the Google Earth Engine. If you are most used to Python, you can use this Python API, which is the EE, directly. You don't need to come to R to do that. But I use R on my day-to-day, so that's why I have to do this. But it will be the same syntax. So if you are more into Python, you also learn how to use the Google Earth Engine, and you can use it on Python the same way. Okay, so it's not an issue. So this initiative of this package, it's comes from a lot of people listed here. It's also listed on their official website from the GitHub. You can take a look on that. It's a very interesting website, and they also provide a website with more than 250 examples that you find this link in the script on different stuff, from images to image collections to lots of a diverse type of stuff you can do with RGE. And they also provide some help on installation. If you see here this part, this EE install, this should be the easy way to install the environment and all of that. Perhaps you can get it done with using only this, but I've tried this on a few machines and it was not installing. That's why I put that whole tutorial and that script which does the installation more manually. But perhaps you can get installed with just this, but I was not able to. So okay, so but if it's already running, then don't care about that. And so why should we use this? Why not use just GE on the official interface in Google, like this this interface? Well, first thing, I think it's because if you use it in R, you can use R language together with the GE syntax. In the Google Earth Engine platform, it uses JavaScript, and so I find it easier if I can merge my knowledge with R, or perhaps you use Python with the GE syntax, and then you can use the RStudio interface, which I find nice to code to run your scripts. So another thing is you can use a more dynamic code. Like for example, if you want to do to filter some images for a monthly interval and download that to run some method, you can think of that about using a for loop to do that one month at a time. But inside the Google Earth Engine, they do not recommend that you use for loops, for example. Um, and so there are ways to do that inside Google Earth Engine, but it involves a different um, approach. And if you use GE inside R, you can do that more dynamically using for loops, for example. And you can visualize the data sets from GE inside R and overlay that with data sets from your own. Like you load your shapefile inside R, you can just plot it here, plot on top of the satellite imagery that you visualize from GE. And making a pipeline for data acquisition from GE to download this data into your Google Drive, and lastly, do any kinds of processing, any methods that are not available at GE. For example, some deep learning that's not still available from GE. You can run random forests in GE. You can run probably support vector machine or more some traditional machine learning methods, but you cannot yet run a deep learning method. So if you want to do that, then you have to download the data and do it yourself on your local machine. So these are some of the advantages that I identify to do that. And now some basic Google Earth syntax. Within Google Earth Engine, you have 4 main types of data. The first is the image. So the EE image is like a single image that you have in space. So single image, and it may have some bands. So it can have many bands. Then you have the image collection, which could be, for example, several now. Well, this is a bad drawing. Okay, but you can see it here. This is like image 1, image 2, image 3. So understand this like, for example, different dates. So you have a stack of these images with different dates, like a time series you can think about. And you can do lots of operations using this image collection, and we will see it during the course. And you also have the features, which are like some spatial objects like polygons, points, lines. So this kind of stuff. And you also have the feature collections, which could be a combination of different polygons to different points. So different features stacked on a single object. I must confess that I do not usually use feature collections. We use features like shape files, like a single polygons and this kind of stuff to extract data, for example. But I usually don't use feature collection. But for people that work with lots of different shape files, you may find this useful. But I usually work with image collections and features. So these 3 are the main constructors that I use and then I find important. Inside R, for example, you would imagine that this is a raster, and this would be a raster stack, if that simplified for you. And okay, and now some differences from GE to RGE. There are some minor differences. For example, if you look here and you already have some experience in GE, you'll see that this is some strange thing here. That's because in GE we use a point instead of the dollar symbol to separate our functions. So in the JavaScript it's point, but here in R we use the dollar sign, dollar symbol. Lots of times we use the equal symbol instead of the colon as well. The parameters, they do not need to be written between quotes. So you see this during the code. You do not need to state variables in R at all. You don't do that in R. But in the Google Earth Engine, you should say var SRTM, for example. This is an image. In R, you don't need to state anything. I think there's a good documentation for the functions. I will show you how to look at it in a second. And there's a drawback that you don't have the console. So this small screen that you have on the Earth Engine interface, but you can print some information as well. It's not as dynamic as in Earth Engine, but it also provides you the metadata to understand the data. But at the same time, you have the advantage that you can make loops and other nice things. So the last bit of a more theoretical thing here is where to find the data. Like, where do I start? How do I use like Landsat data, Sentinel data, RSTM data? So if you get this link here and you paste it, you see this page that has some climate, weather, surface temperature, climate, atmospheric weather, imagery, Landsat, Sentinel, MODIS, high resolution, terrain data, land cover data, croplands, and all of this kind of stuff. So let's just look into one of these, like Sentinel, for example. Or actually, sorry, I will not click on Sentinel. You can click if you want. I'll click on terrain because this is the next example. So imagine for terrain, what you want is like elevation data. So you see different kinds of elevation data that are inside Earth Engine already at your disposal. So I will try to find the one that I show next here. I think it's this one. NASA SRTM digital elevation at 30-meter resolution. So if I click on any of this on the official website, you see the dataset availability. This is a one-time thing, so there's no variation here. You can see the provider, and you can see, this is the most important thing, the ID, let's say, the name of the data set. So the name of this data set is USGS slash SRTM. So this is the name that you use inside the Earth Engine and inside the R to use this data set. So you can copy paste, for example, this and paste on Earth Engine and R to use it. Directly within Google Earth Engine, if you click on this small button here besides the name, it will rapidly show you some example to look at this data. So just to show you what this code put here, it stated a variable, it loaded the EE image with the name of the SRTM data. So that's what we want to do as well inside R. So going back to R, we see that in the section image SRTM elevation, we see that we have the SRTM variable, EE dollar image, and that name that we saw on the website. So the SRTM. And if we run this, it won't show anything. Just, okay, if you see what's inside this object, like highlighting just the SRTM and running, you see Earth Engine object image. It's an image, and it doesn't say anything else. If you use this function EE underline print with the SRTM object between the brackets, you see hopefully some information on the console. Let's wait. It's downloading information, and now the EE print. Let me open this a bit bigger. Okay, it's showing like the metadata, like it's an image. This is the ID. This is the number of bands. It's just one. It's the SRTM. The name of the band inside the object is elevation. Imagine that if you have Landsat data, you have the band name like B4, B3. So this is where you look for band names. Number of properties. To be honest, I don't recall exactly what's this. Number of pixels. So this is a huge number, and it says approximately the size of this data set. So this is a very, very big number. And why is that? It's because if you plot this with this map add layer function, you see that we are looking for a data set for the whole globe. On the viewer here, you see that's all grayish. You cannot see much of the SRTM. If you zoom in, for example, in Brazil, there's not much here. But we can improve this visualization if we use some parameters. And this is what the next block of code does. Like it set up some parameters, like what's the band? It's called elevation. We saw that. What's the minimum value of elevation? Let's say 0 meters, and the maximum value, let's say 500 meters. So if we run this and we plot it again with, let's just highlight what I just ran. Now we can see something else. We can see a better visualization of the elevation, and this is running for the whole world. I hope you guys were able to run this as well on your end. And if you were, now it's a time to realize that you just visualized, plotted the elevation for the whole world with just a few lines of code. And you can visualize, you can zoom in to any part of the world. It will start to show the elevation dynamically, showing you the resolution. So I think this is like mind-blowing. So do we have for the organization, do you have any questions so far?
Ricardo, do you hear me?
Yeah.
We do have some questions, but it's quite long. I will forward you the question later on, and you see when it will be more appropriate to go into it. Okay.
Okay.
So
Great.
for the time being, you can go on.
Okay. Sure. Okay. Let's
And
get.
just a remark, Ricardo.
Yeah.
We crossed already 100 participants from 3 channels, and
Great.
participants from Argentina, Brazil, Chile, Colombia, India, Israel, Iraq, Mozambique, Portugal, South Africa, Slovenia, Tanzania, and USA.
Wow.
So maybe I forget someone here, but this is what I catch actually from the
That's
chat.
very nice. Yeah. Hope I can teach you something like a world lesson. That's where we live today. Okay. So let's continue here. Now I show you some a different function that helps you visualize the data. Before that, you can also change this elevation. I ask you, play with these numbers here. For example, change it to 1,000, let's say, and plot it to see what you can see differently. So you can play with that while you listen. And so this next function is about just locating a place in the world and setting the zoom and this location like a focus. So I put the coordinates for our country capital, the Brasilia, around that actually. And so if you do that, nothing happens. But the next time you use the add layer function, map add layer, it will already focus on some location. If I change the zoom, like let's say I put 8 here, and I run, it's more zoomed in. If I put a lower number, let's say 2, and I run it, it's a bit farther. So you can use this like to in your code. So I want to visualize my study area. You put a coordinate and a zoom. So every time you run the code and you look at different imagery, it's already locked in your region. So that can help you make things more faster. And the last thing about the terrain is you can usually do some computations in Earth Engine with some inbuilt functions. For example, the terrain slope. If you look for the terrain function, actually, let me try and do that here. At the Earth Engine interface, if you look for the docs file, you can type in, for example, terrain, and you may find the functions of that you have for that. Let's click on terrain, it not happens, but let's say slope. Calculate slope in degrees from a terrain digital elevation model. You also have like hue shade, you have like aspect. So there are some cool built-in functions that you can use. Here I show you an example of slope, a very important terrain predictor. And you can run this chunk of code. What we'll do, it will calculate the slope of the SRTM, it will print the metadata, and it will add the the map to the viewer. So you can see, like for example, in Brazil, where I set my center coordinate, we have some steep slopes here on the near the coast. We have more flat terrain in the Amazon, our flood plains and all of that kind of stuff. And we also have some very, very steep slopes on the Andes mountains. And this kind of stuff also goes for USA and also in more the Asia continent. You see this kind of slopes. So you calculated the slope for the entire world with this comment. And to clarify here, these computations are being done in the Earth Engine cloud processing platform. It's not inside R. We are just visualizing the data here, okay? So it's like an interface to Google Earth Engine. And before we move to the next section here, I'm just to highlight the second link in where to find data, which is this one. Is a link that I found a few months ago. So it's community datasets. If I open this link of this community datasets, you see this GitHub, very nice curated GitHub. And you see like data from population and socioeconomics, geophysical, biological, land use, hydrology, agriculture, vegetation, forest, lots of different stuff here that are not part of the standard Earth Engine products. So, for example, you create a data set based on your study. You can message these people from this GitHub and say, okay, put my data set out so other people can use, like open science. It's good. I like it at least. Okay, so like just one example here. I think there is the hand data set here. Oh, maybe not hand, but maybe height. Okay, height above the nearest drainage. This is an amazing kind of data that there is this representation here that you can use as a terrain predictor as well for many types of studies. For example, there are studies in the Amazon that shows that if you use this product, you can locate the areas in the plateaus, so in on the top of the hills. You can find the areas on the valleys, more close to the water, close to the rivers. You can find the slopey regions, and these are related to plant distribution, for example. And you can use this to study water flow. You can use this to study risk, disaster risk. So lots of stuff with this kind of data, and it's already available for the whole world with 30 meters. You can find the image, the ID here. I'm not sure what is a collection, but anyway, there's a data here you can find. You can open inside Earth Engine and Rge. So this was just an example of other data sets. And people are trying to organize that so we can make better use of it. So the next example I show here is a land cover map made in Brazil. It's called Map Biomass. It's a land cover map for the whole Brazil. It's not a standard product as I told you, so it has like a bigger name here to use it. So let's just load this in R and see the metadata. Okay, it's loaded the metadata for that. And we see here, again, it's an image. This is the ID. This is the number of bands. Now we have an image with lots of bands. So remember, images can have lots of bands. And we have the land cover classification for between 1985 and 2020. So like 35-ish years of data here that you can use it for your studies. And these amounts are around a terabyte of data with millions and billions of pixels. Here are also some metadata from the first band. It usually shows the like a summary and some data from the first band. So it says the project coordinate reference system, the resolution, here it's in meters, the size of this data set, the dimensions, all this kind of stuff. And I note here, take a look at different bands because it's the different years. And now we are going to select one of those bands for visualization. And how do we do that? So this line here is the same line as before, but now we use this dollar symbol at the end. And what this dollar symbol will do is like more or less concatenate the commands that we use. So we get this data set and we then select the one of the bands. So this select function does that for us. If we now run this land cover 2020, we'll get the metadata, hopefully only for the 2020 now. So we can use this to select, for example, a few bands from Landsat or Sentinel 2. Like if you want to get only the Sentinel 2 bands that have 10-meter resolution, let's say, you can select them through this this command. And now here to visualize that, this is slightly bigger than the last time we did with the SRTM, but the thing is, there are many classes of land cover. Like in fact, there are. If I open this link here from Map Biomass, we'll see that there are many classes, like going from forests to natural formations that are not forests to crops to non-vegetated areas to water bodies, and you see the ID as well and the code, the suggested color code for that based on the official Map Biomass color approach, let's say. And so I got all this information from that table and put here for you, so we get a visualization similar to what they show on their platform. So if you run all this code here, we have the colors here, we have the we input these colors in this parameter called palette. I don't know how to pronounce that, palette, but anyway, this palette of colors, it enters here on the visualization parameter that enters the map add layer right here. So reminding the add layer function, the first thing is the data, the image. The second parameter is usually some visualization parameters, and the third is just the name of the, like any name. You can type in anything you want here. It's just the name that shows on the viewer. So if you plot more than one map, you can see different names here. So just to zoom in to show you, this is the land cover for Brazil. You have rainforests here on the Amazon, Brazilian Amazon. You have this more light green ones with the Savannah Cerrado region, which is very, very big as well. We have some remnants of Mata Atlântica biome. We have the Pantanal region here. And we also have the agriculture, if you're interested in studying that, and all these other land cover. And if you zoom in a lot, you see like it's very detailed. It's 30-meter resolution. You see up to the best resolution it can get directly from inside R. So I find this also amazing. I also put a note here. You can then plot your own shapefiles on top of this view to visualize land cover. And I'll show you how to do it on the next step here. So another exercise that I put here for this section is, now let's also get the first land cover map that we have within this product, the 1985 map. And we do the same thing, but now selecting the 85 data, and we plot them together. And to do that, we just use a plus sign here. So it's map add layer, the 85 with 85 name here, the 20 name here, and a plus sign. So when we run this, we should get the two maps plotted on the screen. Okay, let's take a look on one of the states that's quite peculiar here, Rondônia state on the southwest Amazon. You can see on the yellow are croplands, and this is the 2020 map. I'll try to show this a little bit bigger. And when we unclick this 2020, we'll see the 85. So it's a quite drastic change. I find this kind of visualization at the same time amazing and sad in the way that the forests are being consumed. But okay, let me go forward. You can use this for your studies. I think it's a nice, amazing data set and way to visualize this. Okay, let's move to the next section. Now, I'll show you an example of a precipitation data set and how to extract some data directly from Google Earth Engine and plotting and actually grabbing the data from the Google Earth Engine and plotting on your screen. So for this example, we load a shapefile that is from USA. You can expect that this was from one original example from my RGE that I copied. So that's why it's on USA. But anyways, just to show the example, we get this. You can enter your own shapefile to do that. So let's just take a look inside the NC object. This NC object is some polygons. I can plot the NC object as well with plot. You see are some polygons. ST geometry, just some polygons. You can use your own polygons. You can use your study area to extract the precipitation. And now we use the precipitation data set from the TRMM. To find it, again, let's go back to the original Earth Engine catalog. If you don't find the website where to find data, you get this link here. You enter it here. And I put here, you can enter rainfall, for example, if you don't know the name of the product, but I already know that TRMM has a nice product. and I find here TRMM 3B43 monthly precipitation estimates. I click it here, and it says to me, okay, this is the ID that you should use. And if you are not sure how to use it, you can click here on this square and get an example inside the Earth Engine and take a look. Also, in these web pages, it's quite interesting that it shows a description of the dataset, how it was created. It also shows the bands, like for example, we have precipitation, relative error, and some weighting. It showed the units, which are very important, and also some minimum and maximum values. So this is the ID we are going to use. Let's see if it's the same ID that I use it. Yeah, it's the same ID, 3B43 version 7. Yeah, it's the same thing. So again, we just load this thing here and print the metadata. Note now that this is an image collection. It's not the image that we were working up to now. And now when we look to the metadata, we'll see that the first it shows the image collection metadata, then it gets the first index, the first image of the collection, and it prints the image metadata, and then it gets the first band, the precipitation, and it plots the band metadata. So you can see get some understanding of what's inside this object. For this image collection, we have data for 264 different dates. And in this case, since we already know it's different months, so it's 264 months. It's already telling us that the start of the first band is 1998. And so this is just the first image. So this is January 1998. And if we look on the product description here, we see that it goes up to 2019 December. So we have all of these months inside. And okay, now we have a bigger chunk of code. Let me explain what's going on here. Imagine that you only want to get the precipitation of 1 year. And we have data from 1998 to 2019. So it's like 20 years or something. You can specify the date using this function called filter date. And the filter date enters first the start of the date and the end of the date. On this example, we use a slightly different syntax. We use these things here, which in R, they are called pipes. So these pipes, they also connect the commands, the functions, and you can either use these, or you can also, let me show you an example here. You don't need to do this. You can also use the $sign, and then you don't need to specify these again. For example, you could just do, for example, this part, excluding this first bit and the pipe, and swapping it for a $sign and without the stating image collection again. So it's two different ways to do this. I usually use this more simplified, more shorter one, but you may find the codes in the internet with these two different notations. So in this example here now, we get data from January 2001 to January 2002. We also select the precipitation band from inside the product. Remember, we had precipitation, relative error, and something else. And to do that, we use a map function. I will explain a bit what's that. And we also have this two bands function, which translate from image collection to an image. I'll explain a bit what's this. And the rename function, which will just output like this 1, 2, 3 up to 12. So what's happening here? Let me draw. I like to draw stuff, so get used to this. We have an image collection here. Each image is a date, like month 1, month 2. Then we used the filter date to get just the 2001 data. Then we use the map function to select only the precipitation data. Now we have what we have here. We should have 12 images of precipitation. But these are still an image collection, and these bands are separated. And what these two bands do is like it translates from this image collection to an image, and now it's a single EE image object. So that's what these two bands command do. And the map thing to select the precipitation, it works like this. If you have an image collection here and you want to do a function for each image of the collection, you must use this map function, which will be like a for loop. So imagine if you do like in R for loop from I to, from I in 1 to 12, let's say, and wow, this is bad. Okay, like this is a for loop that you only get the precipitation out of the of our data. So what this map do is exactly this for loop. So the map is basically a for loop inside the Google Earth Engine. It's how the Google Earth Engine developers want us to use. That's the more efficient way to compute that inside R. So remember, map equals to a for loop inside the image collection, looking for each image. This is one of the most important concepts of Earth Engine codes. So if you don't understand how the map works, please write on the chat. I can explain again. Meanwhile, I'll move on. So you can run this to get this data. Actually, if you run this part, it's not yet getting the data. It's still on Earth Engine, but it's selecting the data, doing this filtering for us. And now, with this next code, the extract data, now it will indeed extract the data from Google Earth Engine to your computer. And this is done through the EE extract function. If I push F1 to get the help of this function, or you type in this in the console, you also get the help. You can also type in this search box in the help, and so F1 in the EE extract, you get help. Okay, extract values from EE images or image collection objects. It's similar to the extract function from R that you can extract data from an image, but this one, it extracts directly from the Earth Engine. All right. So what are the parameters for this? So the first parameter is the image you want to extract the data from. The second parameter is the are the geometries, the features, the feature collections, the spatial objects, the polygons. You can think about the different names to call the polygons that you want to extract the data from. So when you run this extract data line, it will take a while, a few seconds to a minute. It will show this message in red, which may be a bit scary, but not all red messages are scary. The data is already here on your computer. So remember this area here on the United States. We got the precipitation for this area, which is the second parameter here on the function. So TRMM polygon, we got the data. And this last bit of this section, it plots the data. I hope you don't get errors with this. I usually don't use this kind of function to plot, the ggplot. If you get some error running this last bit, maybe it's an error telling you, oh, this package is not installed. Then you have to use like pload, the name of the package, and you install it. But when we run this, we get on the plot screen this data plotted to us, which is the precipitation. Let me try and maximize this screen. Hope it works. It's all white. Okay, very big. It's the precipitation for all of that polygons from January to December 2001. Yeah, and you can do the same thing very fast to look for your study area. What's the precipitation in my study area in India? Let's say you can have the polygon, you extract it. What's the precipitation in the middle of the Amazon? You make a polygon there, you extract the precipitation. No biggie, it's quite fast to do that. So if you have any questions about this code, you can type in on the chat as well. And I think someone already asked here, I have on my laptop here, if this video will be saved on YouTube for future watch. The answer is yes, it will be saved. So I know I'm quite very speedy on showing this, but you can watch it again, and if you get some error, you can run it again. It will be all fine. Okay, so if we don't have any urgent questions, let's move to the image collection Sentinel data. So this is getting closer to our last application of today. Let me clean this thing here so it's a bit simpler. Let me clean here as well. So now what we want to do here is to filter and visualize Sentinel-2 data, but at the same time we want to do cloud masking. We want to do some different things that we will see ahead. So the first thing is the cloud masking. This function here, mask S2 clouds, I did not write this from scratch. Like, I'm not the author of this. There is a version of this function for GE. It's slightly different than this, but very close, very, very similar. And the guys from Rge already translated for the R code. And what it does, it gets the band from Sentinel-2, the quality assessment band, and it applies some computations to see if that pixel is cloudy or not. And if it's cloudy, then it will remove the cloudy pixels. So you run this function, it will not return anything. It's just the function that we will apply on the next block of code, which is actually here, just below the mask2 code. So first thing, the ID of the Sentinel data. So if you didn't still get how to find this, we go where to find data. We have this website. We entered here. Type in Sentinel. See what's up with Sentinel. There's Sentinel 2 level 1C, Sentinel 2 level 2A, which is the most processed level. LL1C is a bit less processed. Let me remind which one I use here. Okay, I used the S2 SR. Let me see which one is that. It's the S2 SS, the 2A version, which is the most processed version of the Sentinel-2 data. Of course, you can see the bands here, as I told you before. Like, what's the most accurate bands here? The smaller pixel size. Band 2, band 3, band 4, band 8. And to highlight here, this small line here, QA60 cloud mask. So the cloud mask function will use this cloud mask from the original data to apply it to your imagery. So let's run this and take a look of what's the output. Here we use again the more simple syntax with the $sign and just the functions. So again, we use filter date. We get data from November 2019 to January 2020. So there is November, December, January, 3 months of data that we filtered. There is the possibility of using a pre-filter to get less cloudy tiles. So this cloudy pixel percentage is a property of the image collection. It's inside of the image collection. If you type in the number here, let's say, I'll just tell you this. Okay, with this 20 number here, 20% clouds, it got only the data that is less than 20% cloud before applying the cloud mask. So if you see the metadata for this, it returned to us 178,000 images in this image collection. So it's a huge number of imagery. And this is for the whole world, okay? We didn't set the area yet. If I change this number, let's say only 10%, I'm more conservative. I want to get just the best of the best imagery. 10%, let's see how this number drops. Now we have 132,000 imagery. So we dropped from 178,000 to 132,000. So you can see the effect of changing this parameter. So I will still use the 20. I will not run the ePrint again because it's already done. And now let's look at one specific location on Earth. It's a location on South Brazil at Lagoa dos Patos, translated like duck pond. So I made this polygon over this area. So this is the bounding box for the polygon in latitude, longitude coordinates. So let's see where this is located in the world. Is this small rectangle here? When we look at it, so this rectangle here on the southern Brazil, we translate this object, which is a Earth Engine geometry polygon. We translate it to a feature. Remember that one of the basic constructors. So we translate it to a feature. Now if we see, it's a feature. And we can also use this get info function to get some information out of these objects. Like what's inside of this? Oh, it's type, feature, polygon, there's these coordinates. So it's an interesting function to use to explore what's inside of the objects that you get out of the Google Earth Engine as well. So now for this next chunk of code, we filter our image collection for this area, this specific area on the South Brazil. Afterwards, I invite you to try and put your own coordinates here to look at your own area. But for now, let's look at this same area so we get the same output. And how to do that? We use the filter bounds function. So I know that's a lot of new names of function here, but you see that you use always the same ones. Like you want to filter this data for next application, it will be the same names. You just copy the code, paste, and change the polygon, change the dates, and you use the same basic code. So the first thing here, filter bounds. What does it do? Let me say here. Imagine we have these. Perhaps I show here at this bottom area. We have this area, big red area here. Imagine I have lots of images here, lots of tiles from Sentinel, and it will check which of these tiles match our polygon. And I would say, okay, all of these tiles match the polygon. Imagine all of this match. So we will have like 1, 2, 3, 4, 5, 6 different tiles matching the polygon. When we do this filter bound function, it will return then to us only these 6 tiles. So you're already reducing the number of tiles you have. Now, so this is the filter bounds. Okay. The second thing we do here is the map. So remember what I told you about the map? The map works as a for loop, looking for each image inside the image collection separately as a for loop. What it will do is apply a function over each image to clip the image using the polygon that we have. So now if we have these 6 matching tiles for the area, but let's give an example. This is the polygon, and now our matching tile is over here. This is one of the tiles, okay? And what this clip function will do, it will look for this specific tile, one image at a time, as I said, and it will clip this image of this tile for this location. So it will return only this part. So this is the clip. So we match these two functions. So first, we reduce the number of images for the computation, and second, we clip the image exactly through your area. And then we'll have different pieces of images. Perhaps one piece is this part, perhaps a second piece is only this part, and we have this puzzle, let's say, different images. So we do this, we run this, and we see now how many images do we get out of this. Let's check the metadata. Now, for this specific region, filtering for our region of interest, we have only 18 different images in our image collection. We can see the bands of the Sentinel 2. We can see some information of the first band as similar to before. What we can do with that? Well, first thing we can do is just plot one of the images to see what we have here. To do that, remember we have 18 different images in the image collection. We want to plot only one. It's not as simple as plotting a raster, the first image from a raster stack as in R. In R, you will do something like, let me draw a bit bigger. You do something like R equals to stack of, let's say you have the data here, and then you imagine you had like 18 imagery here, and then you would just do R 2 square brackets 1, you get the first image. This is quite simple, but in the Google Earth engine it's a bit more complex than that, but I already have the code here. You can just use it. The first line here, it gets the number of images inside this image collection. So if we see the output of Sentinel-2 data n, we get the number 18. Perfect. How did I do that? I use the getInfo function. So if I run just the getInfo, I will get lots of stuff that's inside the metadata from those imagery. And what I did, I entered inside the metadata for the feature attribute, and I got the length of that. So how many different images did we have inside of that? Do not confuse these features with the imagery. This is just an internal name. So these are images and not features. So we have the number 18. And why is that important? Because we use this number 18 to create a list of imagery. And how do we do that? We enter with the object, with is an image collection. We use the toList function to make a list, and the number of items inside this list is equal to the number of images we have. So if we do this part only, we have a list now. And each item of the list is a different image. And then we tell R, get the 10th item of the list. And if I am correct, these lists usually start with 0. So the first index of the list is 0. So let's try with 10, then we test with 0. So all of this inside this thing here, it's a computed object, but we know it's an image. So we state here, image. So when we run this, now we have just one of the 18 imagery. If you don't understand exactly what's the programming part of this, don't worry. You don't need to type this again. You can just use this code, change the numbers, and be happy. And let's see the metadata inside this object. All right, we have now an image object with 23 bands. Yeah, that's it. And now we want to center our map to the feature, to this area that we were looking, and we want to plot this image, and we can choose which bands we want to plot. In this case, I chose the band 4, 3, and 2. Let's see if I can see in the page we opened before. Band 4, 3, 2. Band 4 is the red. 4, 3, 2. 3 is the green, and 2 is the blue. So it's a red, green, blue composite. It's a true color composite. And we specify a minimum and a maximum value to plot. Because if we do not do that, we will have the same output as the first SRTM plot. It will be like grayed out. So Let's plot this. Hopefully it works. All right. We see here the first image of our image collection. It's just the not the first, the 10th or perhaps 11th item inside the list. So it did not cover all of the region. The region comes a bit to the left as well. So let's now change to 0 to see the first item of the list. Let's see if that works. So this image covered the right portion of the area. Let's see where is the first image of the list. Oh, it's covering the left portion. So the item 10 inside the list was covering this part. The item 0 is covering the left part. Because most probably there's different tiles of Sentinel 2 covering the same area. So if you were to download this directly from the Copernicus website, their platform, you likely have to download 2 different tiles for this area. But I'll show you how you can skip that process with the Google Earth Engine and just do it once. I put a note for you to try and change the get inside the thing here. Let's just test, let's say 17 should be the last item. I will skip the EE print so it's a bit faster. Let's see the 7th item. Oh, this is good. The 17th item inside the image collection was the last image. It had lots of clouds. So these white areas were clouds that we masked already with our mask as 2 clouds function. So that's why it's all white in here. You should probably see still some effects of clouds because these masks are not 100% perfect, but still they're quite good. You remove most of the problem and should help us to do the next part of the process, which is making a composite. Okay, if you have any questions, I see there's not many questions, but write down your questions, put on the YouTube, put on the platform you're watching this, and this is where I think the Google Earth Engine platform really shines, which is making image composites. Because imagine you want to study the month of December for this area and it's all cloudy in one image. On the second image, you have data over here on the north part, but you don't have on the south. On the next image, also in December, it's a bit better. So there are ways that we can merge this imagery and merging only the good parts of it, the parts without clouds, to create a composite. So in the Earth Engine terminology, usually when you do that, when you compile different images from a collection to a single image, it is usually called a reducer procedure. We use a simple reducer procedure here, which is the median function. So the median function, it's a statistics thing. We can also see in R, for example, the median of a vector that has the values like 1, 5, 10, 3. Let's put a very different value like 200 here, like an outlier. Let's put another like 20. If I have all these values and we have this outlier here, the 200, let's say this was a cloud pixel. If we type in median, we got 7.5. So you can imagine that the median function, it will find what's the most frequent value of the distribution of different values that you have. So if you have different images covering a period of 1 month, some of these imagery are cloudy, some not. When you do the median of a single pixel for the whole imagery, pixel by pixel, it will get you the most frequent, not the most frequent, but a value that corresponds around the most frequent value. And this is what we'll do on this next chunk of code. It's the same thing as before up to here, but now we add the dollar symbol and median. So remember here what we are filtering. This is November to January. So November, December, January. So 3 months. You can change this. You can put just 1 month if you want, and make a monthly composite. But in this example, I'll show you if this 3 months. When I run this, let's see what we have from the output. It starts as an image collection. And the output, it's an image because we calculated the median value between all of the different imagery. So drawing, just to make this very clear, we had this image collection, and then we applied the median of the image collection, and now we have one single image with the median value per pixel. So like imagine this went here, this went here, this went here, calculate the median, and now this pixel is the median value of all pixels from the from the image collection. Sorry about that. So this is how you do a composite with Earth Engine. It's quite simple and very powerful. To plot it, we'll just plot similar as before, the same code. You just enter with the image, you just put the bands you want to plot, minimum, maximum value, and this is just a name. You can put anything in here. And when I plot this, now we have an image covering the whole area for a composite of 3 months from 2019 to 2020. You can zoom in. Let's see what we get here. We get some issues here. For in this case, perhaps this left part was more cloudy between these dates, but it's a very common procedure. For example, when you get like MODIS, oh, the green is not good. When you get MODIS data at, for example, 250 meter resolution at the Amazon, which is very cloudy. So you want to get the best pixels out of it, the pixels that are not cloudy. So you do the composite and get the pixels that are not cloudy to use for your application. And now let's take a look here. We have 2 sections left. We'll do these 2 sections left, and we'll do a small break to go to the bathroom. So let's do this part. So now a very common vegetation index. So most of the times you have lots of bands, but you calculate vegetation indices to summarize the information and to study, for example, vegetation. Ndvi, for example, is a very common index, and it uses the bands 8 and 4 from Sentinel. So let's take a look again on the website here. Band 8 is the near infrared. Band 4 is the red band. So the near infrared uses the near infrared, the Ndvi uses these 2 bands. And how to calculate it within Earth Engine? there's already a function that's called normalized difference, which what it does is it does the first parameter minus the second parameter divided by the first parameter plus the second parameter. This is a normalized difference. If you use the Ndvi here and the red band here, you get the Ndvi. If you use what did I wrote here? I didn't wrote the correct thing. If you use the near band here, I'm sorry. If you use the near band on the X and the red band on the Y, you get the Ndvi. If you use a different band, you can get a different index. So for this case, we calculate the Ndvi. This is the function that we will apply for each of the images. And again, our very similar code. And now we added this map calc Ndvi inside. And again, why did I use the map function here? If I were we were given a more synchronous lecture, you guys are answering, I would expect you to answer because it's an image. Oh, sorry, because it's an image collection. We want to apply the Ndvi function for all of the different images inside the image collection. So we do that for the image collection, and then we calculate the median Ndvi out of it. So let's do this and see what's the output. The output again, image, because we calculate the composite, we took the median value. And now we have here also a new band, the Ndvi that we just calculated. And we specified here the name. If you calculate a different index, you can just change, for example, this name here with anything you want, the name for the index, and you can calculate that. And you may ask, oh, if I want to calculate a different index, like EVI, for example, how do you do? I'm not sure if there's a inbuilt function to do that, but if you search for Earth Engine, calculate EVI, for example, let's hope, calculate annual EVI vegetation index in Google Earth Engine. Let's hope someone very clever put the equation for us here. And here we see like there's a how to calculate that inside Google Earth Engine. Like you select different bands, you input an expression and you calculate. There's another different way, more simple. Let me try Ndvi because I looked this yesterday. There is a quite simple way to calculate this stuff here. This line is showing how you do this math with the different bands of the imagery. For example, you can do like one band, subtract another band, divide by one band plus other band. So this is Ndvi. This is a normalized difference index. If you want to calculate EVI, just look for the formula and you can type in like one band plus another times another. You can just use this kind of syntax to do that. I think it's a bit simpler than that previous example. Okay. Hope you guys are following. Now, let's plot the Ndvi. If you are following up to now, say something in the chat that I know I'm not alone here. Hopefully, your guys are also being able to do this. We see here in the viewer. Someone want to say something?
No, Ricardo. It's just there are some questions in the chat.
Oh, sure. Let's go.
Yeah, Rayana is asking if the value of the pixel is 0 or not assigned. when a given pixel has clouds. What is actually the current value?
Okay. From this function that I told you here, first we filter the images with less clouds, then we assign a known value to the clouds based on the cloud mask. And when we calculate the median, it's just, okay, look at all the available values and calculate the median. Usually the cloud pixels will have, for example, a very much higher value. Because the signal is much higher in the clouds. So when you calculate the median, it will get like not the cloud value, not the lowest value. You'll get like the median value. There's a different approach to doing this, is calculating the minimum value of vegetation index, for example. So there are several ways to do that, but we hope that this mask works, and we calculate the median, which smooths this process, and hopefully we get a good composite.
Perfect. There was another question here from Saleti Gertner. She asked about trim data, but it was answered already by Danielle. She asked about the trim temporal resolution. So Danielle answered that there is one monthly and another product with every 3 hours.
Great. Anything left?
Rihanna also about map biomas. It was answered actually by Leonardo Biffy. She asked if this is a global data set, and he answered that actually just for Brazil, but there are actually some other global products about land cover. That
Yep.
one released recently by Esri, right?
Yep. For this person, you can look at the where to find data, like the first website, and you can type in land cover. There are several land cover products out there.
So then let me check. So there is another question here from Ana Carolina Pessoa. She's asking, is there something similar to the inspector from Google Earth Engine to be used in the map inside R so that we can explore values of specific pixels?
That's a great question. Thank you, Anna, for the question. To be honest, I don't know. I thought about this when I was creating the presentation, but I didn't have time to look for it. But I had the same feeling. Okay, but I want to know what's exactly the value of this pixel on my screen. I suppose there is a way to do that, but I do not know. I can't answer right now.
We can check that and answer it actually later, and if someone of the community here knows, can also write on the chat.
Yep. Anything else, Feraldo?
I think that is actually all.
Okay.
There is one here. Is map biomas an image or and not an image collection? Why?
Why? Because how they created the product, they put each of the different dates as a band of the image, and not as a different image.
Mm-hmm.
I'm not sure exactly what would be the difference. Like, just say each image is each date is an image, and then you stack as an image collection. I suppose it will be a similar thing. Um, but in their case, they put as different bands. But it's very similar.
Perfect. So actually, they're all.
Okay, great. If you have more questions, just shoot and we will keep answering later. So the last thing about this script is, okay, I have the Ndvi here. You guys are probably visualizing it for this area. You can play it for another area later. But how do I get this data to my computer to do some analysis? Or what can I do with this data? There are methods to use to use like classification methods inside Earth Engine, like random forest, for example. If I type in Earth Engine random forest how to, I'll find here some guides how to do random forest from inside Earth Engine. You just have to adapt the basic code, but it's quite simple in the sense that it's like this is the line that train a decision tree algorithm and then classify the image. You can do this stuff inside the Earth Engine and just get the result. Okay, but for my work, I usually don't use these tools. I like to use my own methods, like the deep learning that we will explore next week. And to do that, we need to download the imagery. Because the Earth Engine do not yet allow you to input your, as far as I know at least, that your own algorithm to the platform and run whatever you want. It's based on their tools. So if you want to run anything else that's not on the platform, the way to do it is it's downloading the data to your Google Drive, then to your computer, and doing on your local computer. On the next lecture next week, I will show a path on the middle of the way, like it's still on the cloud, but which is the Google Collab platform, which you can use our code in the Google Collab and get like GEE. Then you have the Google Collab platform using inside R, and then you can get the data similar, the same code that we're using here, get the data to your Google Drive, and then you don't need to download it, and you can use this data directly within the Google Collab. So you don't need to download the data. This is one approach. But if you want to run more heavy algorithms that perhaps this Google Collab platform still do not allow you, then you can use this approach where we download the data and process on our computer. So what we'll see on this last bit here is how to export the data from Google Earth Engine to Google Drive, then get it out of Google Drive to our computer with just these lines of code. So you don't need to open the Google Drive, you don't need to do anything else, just these lines of code. And how do we do that? We have this function here called image to drive. I put on the help, I push F1 here, and I get the help of this function. So what it does, creates a task to export an image to drive. So the first parameter is the image. You can input some description, just a name for the task, a folder inside the Google Drive that you'll be putting this data in, the name of the file that it would export. Imagine you export Sentinel 2, you can put Sentinel 2, the month of the data, or it's a rainfall TRMM data. You can put the same thing, different name. And what else we usually do here? We usually input the scale, the pixel size of the data. We usually put the region, which is the feature that we created before, with this function geometry. So it's now a geometry. Usually put this. And very important, very important, max pixels. And this max pixels thing, if you do not uh, put this here, it will get an error. You get an error from Earth Engine say, oh, this is more than, let's say, 5,000 pixels or something. But we know we are working with millions of pixels here, so we put just a very big number here, and say, get it all for us. So another thing here, I added this thing here, the select Ndvi, because inside this object we have all the Sentinel bands and the Ndvi. So I just added here the Ndvi, so it's a bit faster to download. And when I run this, you can already put this to run. It just it will do nothing on your screen, like nothing happening. But when you run this next line, EE monitoring, it will try to understand what's going on inside Earth Engine and whether your data is being exported from Google Earth Engine to the Google Drive in real time. So these messages will keep appearing like polling for task every 5 seconds. And while this is appearing on your screen, it means that the data is being exported from Earth Engine to your drive. This for this area, it took 8 minutes for me. I did it yesterday to test. And so just keep it running, and we'll just look at these last two functions and then do a small break. So this EE drive to local, I will look for the help function here. It says, move results from Google Drive to a local directory. So essentially, it downloads the data from Google Drive to your computer. So if you're working, you want to work with the data in your computer, want to download the data and work very safely in your environment, don't need internet, don't need anything, it's already on your computer, then you run this. If you're using Google Collab, for example, if I remember correctly, there's a slightly different function, or perhaps it's the same one, I don't recall, but it will download the data from the GEE inside the Google Collab platform, for example. Or if you're using a different virtual machine, like from Amazon Web Services, it will download to a different machine, to your virtual machine. But in this case, we are getting the data then from Google Drive to our local machine. So these functions download the data for you. So you don't need to worry with going to the Google Drive, opening and finding the data. After this finishes, the data will be there. You run this and it will download the data. And this last bit is just a small R code to get this data out of a temporary location. That's where it will be downloaded by this function. And it will place the data in any directory you want from your computer. So I for example, put in my hard drive letter E. You can put anywhere, like you can change to D, C, I don't know. And you can put another folder like test, let's say. Just make sure to use the 2 backslashes here when assigning the directory, or we'll get some errors. So just remove this. In your cases, you should probably reassign this to download the data to your own hard drives. So this is it for this script. Do you want, Veraldo, what do you think? We do the break now and then proceed with questions?
Yes, it is possible. There is only one short one. I will put it here on the screen.
Okay.
Is there a straightforward way to obtain a dataset? Most probably using here a shapefile from the Sentinel for a given region of interest, and at a pixel of 10 by 10. Maybe he wants to know if those pixels or those spectral bands with coarser spatial resolutions can be resampled and then downloaded at 10 meters. I guess this is the question from Ivan Milanes.
All right. Thank you, Ivan, for the question. Yes. If I remember correctly, when you specify the scale here, it will already resample the data. I would suggest you to test this. For example, you remove this, pick a small area just so it's not a very huge file. Then you don't select only the Ndvi, and then specify the scale 10 and see the results for the other bands. I think they will all be resampled. And the other thing about using a shapefile, yes, also. In this case, let me go back here. We use this region of interest, this bounding box. But if you have the shapefile of the region as a SF object inside R, like you can input the SF object directly. I think.
I guess it's also possible to make as asset, right?
In the when you use it from R, you don't need to make the asset like inside Google Earth Engine. You can create it directly here. And to do that, I think it's EESSF. Or is the opposite? Let's check. No, this is the opposite. EESSF. I think maybe it's SF as E. Let's find out. SF. SF as EE. So if you have the shapefile loaded as an SF object, and just to show for people that have no idea what's an SF object, it's the package. It's a package to open spatial data in R, like polygons, shapefiles. If I remember correctly, the syntax is something like sread. Then you put the shapefile name. Let's say this is my shapefile. And then what you would do is like SFSEE of my shapefile. I think it's something like this. Load in as SF object with this function, and then you convert it to EE object. Then you can use it instead of the bounding box. So leave this at the screen if you want to test it out after. So shall we go for the break, Veraldo?
Yes, yes.
Okay, I think 10 minutes. Is that good?
Yeah, I think it's a good time.
Okay, so if you are still running, try to get up to date. If you have more questions, write them down. And after 10 minutes, we go back with the second script.
Perfect. I will just remove here and then let me know once you want to start again then.
Okay, fine.
So we will just make a break. I will just add here Raul Feitosa and also Daniel. If you both want to say some message in between, please take the opportunity.
No, just one question. Ivan or Ivan sent a question, wrote a question right in the beginning. It's a quite long question. Actually, I think it was 2 questions. And I think we should forward this question to Ricardo.
Perfect.
Could you do that, please?
Yes, yes. Okay.
Okay. So I will take advantage of the break right now, okay?
Okay, perfect.
Okay, see you.
We will start then shortly.
Que satisfação falar com vocês, dar as boas-vindas ao evento, dizer que a UNO Chapecó, nos últimos anos, com seu foco na pesquisa, no desenvolvimento da inovação como instrumento de desenvolvimento da região, acredita muito em atividades como esta, um evento importantíssimo que trata de sensoriamento remoto, que trata do uso de plataformas não tripuláveis para atuar principalmente na área agrícola, né? Uma área que nos interessa muito. Nós somos uma região que produz muitos produtos, uma região da agroindústria fortemente constituída por nossas cooperativas, nossas associações, e por isso fica aqui o nosso sentimento de felicidade de participar desse evento. Desejo que seja um sucesso, que possamos trocar muitas experiências, conhecimento e desenvolver essa área. Sucesso, parabéns a todos, sejam todos muito bem-vindos, em nome da UNO Chapecó.
Olá a todos vocês. É uma honra dar as boas-vindas aos participantes deste evento, que é estratégico para Santa Catarina, para o Brasil e para o mundo. Destaco que localmente estamos organizando este evento junto com a UNO Chapecó, que é motivo de orgulho para nós da Universidade dos Catarinenses. O evento conta ainda com o apoio também da Fundação de Amparo à Pesquisa de Santa Catarina, a FAPESC. O evento nos orgulha, já que a UDESC vem melhorando a sua classificação em rankings importantes internacionais, graças aos investimentos que temos feito, principalmente nas áreas da pesquisa e inovação. E a temática do evento de utilizar drones na agricultura e na silvicultura vai de encontro a isso. Dito isso, em nome da Universidade do Estado de Santa Catarina, que tem como missão formar quem transforma Santa Catarina. Desejo um excelente evento a todos. Muito obrigado pela atenção.
Hi everyone, my name is Cheryl Rose Reyes and I currently serve as the president of the Isprs Student Consortium. I am very happy to welcome you all to the 7th edition of the IEEE GRSS Young Professionals and Isprs Student Consortium Summer School this year. On behalf of Isprs and the consortium, I would like to thank all the organizers who continue to persevere in developing this virtual event in light of our current global situation. This is the second virtual edition of this summer school. I would like to introduce you all to the Isprs Student Consortium. We are the official representation of the youth to Isprs. Our main goal is to link students, young researchers, and professionals worldwide interested in photogrammetry, remote sensing, and spatial information science, and to promote their scientific and professional developments. We advocate imaging and geospatial science for informed, scientifically valid, and technologically sound observations of Earth conditions and trends that lead to improved and effective decision-making. I work together with members of the board of directors from all across the globe. Charles from Uganda is our vice president. Charmaine, who is currently in Ireland, is in charge of our newsletter. Mustafa, our social media coordinator, is from Turkey. And finally, Sonia from Azerbaijan is our website administrator. The consortium also publishes an official newsletter called Spectrum, and it is named as such because this publication is envisioned to cover the broad applications of remote sensing, photogrammetry, and spatial information science, and to welcome contributors from diverse backgrounds and fields of discipline. We publish 4 issues a year and from time to time publish special issues. Our most recent publication is on the applications of unoccupied aerial systems for environmental monitoring. One of the major events that we host and coordinate every year are the summer schools. Since 2017, we have been hosting a minimum of 3 summer schools per year in different locations around the world. These summer schools provide opportunities for students and professionals alike to further their knowledge in remote sensing, photogrammetry, and spatial information science at a minimum cost, and to establish their professional networks by providing an avenue to meet and connect with fellow students, young professionals, as well as professors and industry experts. We are again very grateful for the local organizers in Brazil who are hosting the second virtual edition of this summer school, and we look forward to the webinars, the roundtable discussions, and the hands-on sessions. The consortium currently hosts the virtual rooms and the webinar series to provide our community with more opportunities to learn and interact with experts in our scientific community. The webinar series was conceptualized in 2018, and we have organized webinars on Google Earth Engine, computer vision, and machine learning. The virtual rooms was developed by the board of directors as a way to keep the members of the consortium connected during this challenging time and to help them navigate this new lifestyle. All the resources for the webinar series and the virtual rooms are available on our website and our YouTube channel. The Leadership and Service Mentoring Program was launched in December 2020. This program primarily aims to train and familiarize qualified individuals with the responsibilities of the position they are interested in and about the activities of the consortium. We are currently training 6 mentees from different countries who are interested to lead the consortium in the future. You will find most of the recordings of our virtual events over our YouTube channel, and one of our most viewed videos was from the Brazil Summer School last year. The consortium also works in collaboration with the Ladies of Lancet, the Sisters of SAR, the American Society for Photogrammetry and Remote Sensing Student Advisory Council, the Mato Grosso do Sul IEEE GRSS Student Branch Chapter, the Isprs White Elephant Club, and the Asian Association on Remote Sensing in organizing a monthly virtual event called GeoMixer. Inspired by the GeoMixers organized in previous conferences, this event provided a platform for remote sensing scientists at all career stages from around the world to build their professional networks. Finally, we invite you all again to register as an individual member of the consortium and to join us on social media. We are on Facebook and Twitter, and if you need any resources, please do check out our YouTube channel. Thank you very much and have a meaningful virtual summer school.
Hi.
Can you hear me now?
Yes.
I
Now
was muted
I
here.
hear
Sorry.
you.
Okay, I was also muted here. Sorry. So we have here some questions. Maybe Danielle, if you could read here from Ivan.
Which one?
I think the first one is from Ana Carolina Pessoa.
Oh, yes. Is it possible to transform the EE image to a raster image to use air tools prior to downloading the data?
I don't think so. I think you need to because when it's EE image, it's located within the Earth engine, and when we do this last procedure that we were looking here, EE image to drive, then we download it to use at our computer. So only then we can open with like a raster or stack and apply any R function.
Okay. And another question from Ivan. If I wanted to download an image collection, can I have the data with a date column, like a row binding?
Yeah, I think if you manage to filter like a image collection here, I think this would be probably the function to use to download the entire image collection. So EE image collection to local. So I didn't do this with the RGE yet. I've only downloaded single images. Like I make a composite, I download it, and then I do a for loop to do this like several times. I will show this on the next script. But I think probably this function should work for the entire image collection.
Okay. And I have a question from myself. I need to run to create the conda environment like every time I turn on my computer and I want to use the RGE, or I only create once.
Only once. You just create that one time.
Okay, cool.
Yeah. After that, you just to run any application, run this initiate RGE code, like run all this thing here, and it will work.
Okay, cool.
Perfect.
Yeah.
I think the questions are answered. Ivan actually rewrote his questions that he sent in the beginning. So yeah, you can then continue.
Okay, good. So it should probably have downloaded that image on your computer. Let's see if did I run this? No, I didn't run. So I didn't run the part that copied the image to the computer. I run it now. I will put another E here, and this takes a while because it's downloading. If the image is very big, very heavy, it will take more time. So this is just to see the image inside our computer. While this, oh, it's already downloaded. Okay, don't need to wait that much. So the result of this EE drive to local, this F name, it appeared here on the screen. So this the path and the file name that we set up on this previous function, and it exists in this location in your computer now. This second part, file rename, it moves. The function is a bit confusing because it's renamed, but if you rename the path, then you're essentially moving something. Okay, so we move the file from the first location to a second location. And this second location, for example, if I run just this, would be like E in the same name of the file. So I already run this. It appeared true for Mickey, meaning yes, it moved the file. And if I look for this location inside my computer, now the image should be here. So Sentinel 2 data something something. And to open it inside R, I will just copy the path, which is just the E drive in my case. You can depends on where you put the data. I will open it inside R just to show how to do that. Let me put on a different script here, like R raster. Then you put the path with remember always 2 backslashes. You can also use one of the forward slash, but I prefer to use the backslashes because when you copy the path, it's already backslash. So you just add another backslash and the file name. So when I run this inside R, I'm now loading that same image that we were looking here, the same. Let's see if it's the same actually. It should be the same thing we were looking here at the viewer. And the size of this is like, oh, let's see. In the computer, it weighs 350 megabytes. So it's a bit heavy. It's 8,000 by 11,000 pixels. So accounting for a total of 93 million pixels. So it's a very big data set for, because the resolution is quite fine, the 10 meters. You can see also the information for the coordinate reference system. And let's plot this thing in R now. Now this file is in our computer. This is plotting in the plot view. So it's essentially the same thing. The color palette is different. If I change the color palette, I think we can get a similar view. Let's say I change it then to gray colors, and I put 50 shades of gray here. Plot these again. Yeah, it's a very similar plot. Bit different contrast than that one, but we get the it's the same area, and now you can do anything you want with this. Apply any code, any method, anything. Okay, so now moving on to the second script. We have 40 minutes left on this lecture. Let me clean this view, clean this plot, clean this thing here. Close this, close that. Okay, now we are looking to the RGE data acquisition code. What's this script? What does it do? So I had to make a lecture about deep learning, and I wanted to make to work everything on the cloud, like to get the data from the GE, to process on the cloud, on the Google Collab, to apply deep learning and output a result. You'll see if you come to the next lesson next week on the same day, same time, you see that I did not yet achieve that because the procedure of downloading the data to the Google Drive, it's quite lengthy. It takes a while, and I do not know a way yet to apply something more directly within the Google Earth Engine. So we have always to put the data in the Google Drive or in the Google Cloud Storage, the GCS. But then what we can do is select the data for the area we want to do an application, download, and apply the thing in our computer. We can do that. And to do that, to do this experience with deep learning, I developed this script to download the data we wanted. And this will be actually a gift to you because you can use the same script to download your own data, to leverage the for loop that I built in this script to download multiple dates. It will be, you see, it's quite easy to do that. So the aim of the experiment I want to do is it's a crop detection. So it was a rice crop. And I wanted to detect the areas that were covered by rice or non-rice. And so for that, we have some field data, some polygons of rice fields. This data came from Collab, Brazil. It's like a organization that deals with the agriculture in Brazil. You can actually access their mappings in their website. Just to remind, this files is within the GitHub again. So if you are still confused about where to find this, it's on the GitHub. And for example, here we can see algodão, which is cotton in English. And there's 2 states mapped, like Goiás, I think. There are some cotton fields in these locations. Arroz, which is the rice, which is the one I selected. There are many states that have some mapping of rice. I selected the Rio Grande do Sul state, the state to the south of Brazil, and you see this massive mapping of rice. I don't know exactly how they did this. I did not go into details of that. I just assume this is a very good data set to train my algorithms, to train my methods. And then if I want, I could map the rice for the whole Brazil, and hopefully that works. So I'm using data from Collab to represent that process, to represent the rice. And you see there are lots of these areas that's supposed to have rice here. So I downloaded this data set. I placed on the GitHub. Let me find the GitHub here. If you go down GitHub, you see the data set that you can download, or you can just go inside the Zenodo repository here, the link, and probably you can download just the rice dataset, which is this one, Arroz, ARROZ, and download just this because the rest is a bit heavy. So you download this data. We are going to use it on this script. For the next week, I ask you to download everything here, including this very heavy dataset, 2.7 gigabytes. So for now, you can just download the rice one, the Arroz. And we will, with this code, filter and acquire an image from Google Earth Engine, extract the data within the polygons of rice, and also sample areas outside of rice fields as the background, the no rice features, and then we'll train a random forest model in R to use this data and classify the rice fields. Okay, so this is the basic of this kind of big script. So start to run this. We run this first part. There is actually one thing you need to adjust here. You need to adjust the working directory. If you're not into R, don't know very much how to use it, you should put here the location where you will place the field data, that shape files. Okay, so find the path in your computer where you place, like for example, when I open a path and enter any folder here, what I usually do, I click on the path and I copy this and I paste in R and just add back 2 backslashes in each of the backslash. Okay, so do that. Meanwhile, I will run here. Also, adjust your Rge environment for this code as well, and you may adjust the number of cores you have on your processor. To do that, you can run this function. Okay, this function does not exist, but if you use pload parallel, I think it's parallel, maybe. No, it's parallel. Sorry. Yeah, it's parallel. So the library for this detect core function is parallel, Parllel. And it says how many cores do you have on your processor. I put 2 here because most of the not very good computers have only 2, but in my computer I have 8. I can change this number. I'll put like 7. I never put the maximum amount because otherwise the computer may explode. Okay, so moving on. Adjust this path and the working directory, run this part. You can, if you are still using the same script as before, you don't need to run the initiate here because it's already, the GE is already started. But if you rebooted your R, you run the first section again, we go directly to the second session, load field data. So in your folder that you specified as the working directory, you should have the field data. And here it's in my folder. Let me show how it's located within my folder. It's like this. I have a folder called, oh, how do I put zoom here? I don't know. Sorry, it's a bit small, but I think you can maybe see. There's a folder called one field, and then there's the shape files inside this folder. If you put on a different folder, just please adjust here and make sure this shape file is located well. And when you run this, you get like a OGR data source, something, it opens. Don't be afraid of this warning message. We sometimes get some warnings as a slap on the wrist, but we just move on with that. And inside of this field data shapefiles, we can see there are several municipalities. We just get the data from one municipality, for the example, which is called Uruguaiana, the name of the municipality. We transform this to the same projection of the satellite data that we are using. In this case, we are using the Sentinel 2 data. So I put here UTM, the same zone. The data, the CRS, the coordinate reference system you get from the image. I think we loaded before. Let's see if it's still here. Oh, I cleaned it. Okay, sure. But when you load the, I let it here as well. Oh, sorry. When you load the image, you can see the reference system. For example, here, you can copy this information from the image, any image you are working with, and paste here to change, to transform the reference system from one to another. So we just load this data. Here is that command from the RGE package, which Ivan asked about, which enters a SF object, a shapefile, and converts to a feature collection in this case, okay? So you can just run strictly, if the first field data is working, you can just run again this second part of the code. It should not come to any errors. Then the third part of the code, third section, is where we will download the imagery. So this is a part that I told you it's kind of a gift to you, because it's already a for loop that looks for intervals of dates, like for example, from February 2020 to March 2020. And it will download it will get it will filter the image collections for this time period, and calculate a composite for this month. So this will be a composite for the month of February. If you want to download more dates, for example, you want to run a method with multi-dates, like for example for crops, it's very important that your little crop here, it's growing, let's say date 1, let's say date 0, actually, it's just soil. Date 1, you have a small plant. Date 2, the plant is very big. And date 3, perhaps it's a big tree, I don't know. If you look just for one date, like just one, let's say, you may get a good signal. You may classify these against other classes. But if you have the multi-temporal information, for example, you have this month, this month, this month, you have this change across time. And these features may help you to classify stuff. And for crops, that's really important. So using this kind of code, I put an example here where you download from December to January, from January to February, from February to March. So you get out of these dates 1, 2, 3 dates, 3 composites out of this, if you use this code, for example. But we use just one code as an example here, just for February. So we can run this up to before the for loop. So probably row 170. Let's see what we get here. It's loading the samples within the viewer. That's why it's taking a while here. Remember, I told you that if you plot with map add layer and then you put a plus, you can plot two layers of the Google Earth Engine together. In this case, I want to plot, if this ever happens, I want to plot the region of interest, would be like a box, and the field locations. So just the field locations for the crops. So, okay, I'm looking here. If you're kind of lost, take a zoom out. You see Brazil, this blackish thing here on the south. You see like the rectangle and these very small polygons, which are the rice fields inside the municipality of Uruguaiana. So it strangely looks like a bell shape, but or a hat. So these are the rice fields. You can use this viewer also to open some imagery from like some base maps from Esri, for example, to take a look on the thing. But we can also plot the Sentinel as well. So this first part was just preparing the field data as feature collections and this kind of stuff and visualizing. And now inside this for loop, it's the same kind of code you already seen on the previous script, but we do something different now. We leverage the R coding inside this part. What I do here is since we put a for loop here on line 171, we will iterate through this vector of periods to extract and get the I period to I plus 1 period. So imagine I have this is the first, let's say this is I, and this is I plus 1. So we get from this to this, and we do this dynamically within this for loop. If this periods extract vector is bigger, like for example here, like it has several different months, the code would iterate through all these combinations. This with this, and the next loop, this January with the February, in the next loop, January with the March. And you get different months of the same area and calculate the composite. What else does this do? Center the location to our field data, add a plot to the viewer, plot both the field plots on this part with the map from Sentinel, and lastly, it downloads the data to the drive. And here again, we do this dynamically, like we establish the description. We establish the period of the data and the file name based on the this value. Like if this is equal to 1, let's say the file name will be Sentinel 2 data 2020-02. If I had more different periods there, it would then automatically change the file name for me and save everything in the Google Drive very beautifully in this drive directory that we set up in the beginning. In this case, I put like RGE temp3. It will start directly the process to download to the drive. And again, if you have lots of periods inside this variable, it will download it all. So just run this now. This will take a while to run. Let's see if there's a way to do this without you downloading. Okay, this was perhaps you need to download this first. Perhaps if you didn't download the data set. Okay, this is something bad from my part. If you didn't download the imagery from this data set from Zenodo, this .rar file, I think you won't be able to run this next part because you need the imagery. So I apologize for that because this takes 21 minutes to download. It's a very big image. I should have cropped a smaller image. But you can watch the video later and follow this with your own code. So just I'll just put this to run. Actually, I will not run this because, well, I already have this image and this would only take time. But you can leave this running on your machine now. After 21 minutes, you can continue this part, okay? So what this will do, it will download everything to the drive. This next part will copy the files to your computer, also dynamically. This output directory is something we create in the beginning of the script. And in the end, we visualize one of the imagery. So that's why this does not work, because if I don't have def name. But if I look to my folder here in images, I already have this file. It's 1.6 gigabytes. That's what you're going to achieve after you run that for loop and download. Okay, so do that, and afterwards you can run on your own computer. So just to show what's inside of this imagery here on my computer, I type in rs tech, copy the folder, add the backslashes. I put the file name and add the extension .tiff, and it's loaded within R. If we look this object, we see a very big object, 8,000 by 11,000 pixels. If we plot just the fifth band from inside, like first, second, third, fourth, fifth, the Ndvi, which we should see an error because I forgot to put R here. So plot R, double square brackets, and we should see the 50 band on the plot screen in about a second. Let's wait a bit. So we should see this on the screen. This is the area. Remember, the bell shape it's more or less around here with this river and this kind of stuff. So I apologize again. You won't be able to see this part running. You need to download the data first, and then you should be able to run. But I will show you my computer, and then you can follow in later. So what this part section 4 does, for each, let's draw my field samples with this, let's say this is the area. Let's draw my field rise in golden. And what this part 4a does is this. For each field that I have, I get 1 pixel inside of each field. And why do I do this? If I get, for example, every single pixel inside these polygons, I'll have hundreds of thousands, like so many pixels. and I would incur in a spatial autocorrelation problem, SAC, spatial autocorrelation. So if you submit this to the reviewer for a paper, it will bust you. Reviewer will not be happy with this, and so you do not do this. You can try minimize this problem by just getting, for example, 1 pixel inside of each field. And if you have enough fields, that's a more or less a requirement. If you have enough fields, you have enough samples, more distributed across space. So less problems with spatial autocorrelation. So what this first portion of the code, it extracts the data from each of these fields. I will leave it running here, and soon you'll see the location of this is the location of random points. Pick 1 pixel inside each of the field polygons. So these are the lines that we have. Now it is extracting. I will explain the next part while this runs. So the next part, the 4B, we want to get data outside of the field data. So this is now a simplification of the process. Ideally, you have your golden fields of the rice. We already picked the rice data inside 1 pixel each. Ideally, you select, okay, I know that this location in the blue arrow is not rice. This is not rice, not rice, not rice. Okay, nice. But I want to speed things up, and I just did like a more brute force thing where I just make a square and I put I put like random samples across the area, random samples, and then having the polygons here, I tell the script, okay, if the random samples intersect the random samples, you delete them. Now I only have samples outside of the field plots. Nice. Then I can extract them. So this part 4B, it get these random points. On the next part of the 4C, it will actually extract the data from the imagery. So this red is the S2 imagery. For each of the blue points outside of rice fields. And now we have, for example, much more of the blue than the red. This may be a problem for image classification, like underbalanced problem. So I also do a filtering here, like I only have 3 samples, let's say. Then I say, okay, delete, randomly pick samples equal to the number of the target class, the rice. So now I have 3 samples for rice and 3 samples for not rice. So this is rice, this is not rice. Okay, so that's what this 4B and 4C do. I'll just run it here and explain one very nice concept of the 4B. This is something I teach on my spatial analysis modeling classes, which is a way to sample areas with a minimal distance. So you can input here in this RSSI function a minimum distance for that you want to draw your random samples. So for example, we have this window, which is actually this small thing here, this period window, which is created here. And it says, okay, create samples with a minimum distance of 1,000 meters. I think it was the case here. So it will take you, okay, first sample, then I can put another sample around here, then randomly here, then okay, if it's another sample. So you get samples very distributed across the area. So you don't get samples very, very, very close to each other, which again causes the spatial autocorrelation problems, get reviewer 2 very sad, or your dissertation advisors, yeah, all that. Okay, so now we should be able to extract we should be able to have extracted all the data. You can read the code. This is all R. Now it's all R. It's not G anymore. You can take a look and try to understand it. Now we have the data set for rice and other stuff. We visualized it on session 5, and it looks like this. It's a table. Band 2, band 3, band 4, band 8, Ndvi, and the class. It's rice or other. And one thing we usually do for machine learning modeling, we usually split these data sets between training and validation. I will not go much into this on this example, but I will show here how to do that. You can use this code from the caret package, this create data partition with the caret package. It does this kind of split for us, and then we can save this data on the disk, so we can use later with any model we want. Now we have some very nice ways to visualize these data sets. We'll plot 3 types of visualization here. First one is just like density plots that shows the values and the frequency in the y-axis and the values on the x. We can see the rice in red and the other in green. Sorry if you cannot see this, distinguish these 2 colors. It's the basic colors here. I didn't change it, but okay. We can see, like, for example, Ndvi seems to separate the rice from the others. A different plot using box plots, which is very nice to see the distribution of data. For some reason, didn't plot the colors here, but rice has more bigger Ndvi. And the third one, which is also nice, is some scatter plots between the let's hope it plots here on my big screen. Some scatter plots between each band, so you see, oh, perhaps rice has a bigger near infrared and a smaller red signal, which is most likely the case. Bigger infrared and smaller red. So these are very good ways to understand the data. Now, with about 10 minutes left on the lesson, we'll put this inside a model, a very traditional model. So in section 7, I'll just run this. I didn't run the save because it's already saved here on my computer. But what this does is it enters with this train function from caret. Sometimes when you push the help F1 on a function, it appears more than one thing, because some function names are very common, like train. There's a lot of packages that use this thing, but we are looking for the caret package. So you click on the text above the caret, and you see fit predictive models over different tuning parameters. So this package caret is very good for machine learning in R, and this train function, you just change the method here, and it will apply a different method of machine learning. And to check a different method, you can see R caret available models. You find this website available models. You see there's 200 different models here, from like SVMs, random forests around here. I think there's also some neural networks, more simple ones around here. In this case, we use a simple random forest, and now it just ended the run. So to explain how I run this, the train enters a formula, which is the class you want to classify, and this dot is like all the other variables. You can also specify here, for example, I think you should enter like B3 plus B4. If you want to use only this 2, but with a dot, you enter everything. I use the train data set, the method. there are some ways to control for the training, like specifying which cross-validation method you're going to apply. And in the end, you have this fit object, which is where the model is stored inside R. It shows more or less the accuracy for the training cross-validation procedure, like accuracy very high, kappa index also very high. This is not a very difficult classification problem because rice is very different than other land covers. But okay, we have this. And on the section 8, we load the model that we save here. In my case, it was already loaded, but when you run, you save it, then you can load it again on another time, Then you can load now the whole image, and we want to predict the classes for the whole image, okay? So we load it with this stack function. This image list is just the name of the image. If you have multiple images, like a multi-date problem, you can stack all of them as well. You should stack all of them on this stack here. And now I will just crop the area on a small extent to show the results, because otherwise it takes a while to run. So I have 2 extents to run. The first one, I set it here, and I will crop to this first extent. Let me just show what this crop look like. It's just a small image. I predict this. Use the model to predict the rise for this small image. So for that, we use the predict function, enter the image, enter the model. For this small extent, it used only 9 seconds to run, but the whole image is much bigger than this. Took around 30 minutes to run. It's quite a while. So I'll show now the result for the imagery. So this first thing on the screen is the true color composite with the overlaying field data. So don't mind these ones outside of the image because we crop it. But what we see inside now is the rise crop mapping. So we did this nice application. We now know where there are rice croppings. All of those were basically mapped within this extent. We see some errors around here, for example, around here, which overlap some forested areas nearby rivers, for example. When I show you the second extent now, I change it here on the line 400 around it. I will just run the model again. Hopefully it's 9 seconds again. And we see an image more close to a very big river here. There are some rice crops nearby this river, and we see that the model did not a very good job around here, because this vegetation around the river it confused it with the rice crops. I'm not sure if the sample was very good as well, because I did this very over simplistic way to sample, but it showed it did a decent job. We need to further improve to solve these issues. Just a last thing before we finish and answer a few questions. I will try and show you a spoiler. Where is it located? Perhaps it's nearby this course here. Perhaps it's in vegetation. Yeah, I'll show a spoiler of the result for next week that we get out of the deep learning model. So we open this. You won't have this, of course, but I will open this on my computer to show. This is, I cannot get this. Yeah, I forgot the file name. of course. I'll get the file name .tiff. And now I will copy this here. My data is in R. Okay. Perhaps I do R2. Go all crop the R new extent before. That's better. Just put what I did here, just for you to see. I loaded this thing. You won't have this thing here. I will crop it to the extent we are looking. First, let me show you what we were looking with the random forest, and now it should show us. Oh, it didn't work. Why didn't it work? Because I think I forgot to put this R2. Maybe it's not R2 here. It's only the last bit. Sorry. It's just this last bit R2 here. And this is the result for the deep learning model for the same area. This is a spoiler for the next week already, but when we look for these accuracy metrics, such as the accuracy in kappa, the random forest did a very good job. But sometimes when we look for the generalization over a bigger area, we see that it's not a very good job. We needed more samples over here to prove that the model was not indeed very good. But when we look to a result of a model more advanced, like UNet, a deep learning model, we see that in some cases it may give a much better result. And this is a spoiler and already a call for the next week of the tutorial. We'll see how you can go from this image to this classification using deep learning. So again, I apologize for you guys not being able to run this last part because I didn't send you the link of the dataset before. You can run it again, watch the video. And Veraldo, do we have any questions on this last part?
Actually, there is one from Ivan, but it was already answered. I will put it here. Maybe you can comment on it.
Good. Thank you, Ivan.
Then,
You're a very active person. I like that on the classes.
I will add here Raul and Daniel too. And yeah.
Well,
trying actually to motivate actually the participants to write down their questions and comments and concerns, and just to update actually the list so far when people write here on the chat. So participants from Argentina, Brazil, Chile, Colombia, India, Israel, Iran, Iraq, Indonesia, Mozambique, Nigeria, Philippines, Portugal, Serbia, South Africa, Slovenia, Tanzania, and USA. So if I miss a country, sorry, just write down here.
I think you missed Brazil.
Okay.
But it's okay. That's okay. That's okay. I would ask you, Veraldo, to put in the chat or somewhere the link to YouTube where this lecture will be available. Okay. I know that this information was already sent to the attendees, but I think it's not too much if you do it again.
Mm-hmm. Perfect.
Okay.
So is that already?
Okay. Okay. So from my side, I just want to thank Ricardo for the good job, and I look forward for the continuation where you're going to address the deep learning inside GEE. Okay. So I encourage all the audience to join next week on Thursday exactly at the same time. I think this is all from my side. Anything else, Veral?
Yeah, I will just invite Daniel actually for saying some words too.
I just want to thank you for the invite to participate and for the presentation. I learned a lot from the presentation. I used to use the Google Earth Engine in the platform online, and having to know how to use in R is very useful. And looking forward for next week.
Great.
Perfect.
Maybe I say a few words as well to end.
Yes, yes.
Okay. Well, thank you, Raul, for the for the invitation, and also Verado, also Danielle, right? It's a pleasure to try and spread a bit of the knowledge, and we can advance together with this, and having ways to try and follow this big data of remote sensing. Like, it's going so fast, like, and we must adapt and use this kind of platforms to be able to do things fast. So I hope people that watch it from all over the world were able to learn something today.
Sure.
This is definitely for sure. I will just write down here the main web page here of our event. So next week we will have the second module, or the second part actually, of this hands-on. And I just want to invite the participants to have a look on our program. There is another hands-on as well. Let me just check here the dates. So next week, the second module on November 4th, actually, deep learning and for remote sensing images with our language, with the same speaker today, Dr. Ricardo Dallagnol. And on November 9th, so we have another speech entitled Geospatial Analysis to Mitigate the Human-Elephant Conflict in Southern Africa, with Margaret Madden from the University of Georgia. On November 11th, Mathematical Morphology in Processing and Analysis of Digital Elevation Models, with Dr. Daya Sagar from India. On November 18th, a hands-on entitled Global Vegetation Trend, a multi-decade planetary coverage and analysis-ready product, given by Dr. Leandro Parente from Netherlands. And then on November 23, a SAR polarimetry and multi-temporal SAR statistical descriptions with Dr. Carlos Lopez Martinez from the Polytechnic University of Catalonia, Spain. So we have an intensive program. So please register if you didn't, and stay tuned in our events. And please consider also being a member of both societies. That is very important to promote actually this networking. The Geoscience Remote Sensing Society and the International Society of Photogrammetry and Remote Sensing. Well, I will hand again to Raul so that we can close officially then this event for today.
Okay, thank you very much, Veraldo, and especially Ricardo, for the very, very fruitful 3 hours that we spent together. And as I said before, we look forward for the next Thursday. So thank you very much, everybody, for watching. See you again in 1 week.
Okay, then.
See you.
Bye.
Bye-bye.